Greetings, AP Chemistry students. Yesterday we started talking about acids and bases and the Arrhenius and, of course, the Bronsted-Lowry model of acids and bases, which is the one we'll be focusing on the most in this course. When you were looking at some of the work from yesterday, you might have noticed that it's possible for a substance to act as both an acid and as a base. And a substance that can do both is called amphoteric. And water is a common example of that. Let me show you some examples of that in action. All right, so in these two equations here, in this first reaction, HF is acting as the acid and water is acting as the base. H3O plus would be the conjugate acid and fluoride would be the conjugate base. In the second demonstration, NH3 is the one accepting the hydrogen ion, so it's the base. Water is the acid. Hydroxide is the conjugate base of water, and NH4 plus is the conjugate acid. So in the first example, water is acting as a base, and in the second, it's acting as an acid. This can happen with quite a few other substances. Typically, it's ions that have a hydrogen in them and have a negative charge, where you could either add an H plus to it to make it neutral, or you could take away one of the hydrogens from it. Next, we're going to talk a little bit about strong versus weak acids. Strong acids have a large Ka value. Their acid constant is much greater than 1. Weak acids have small Ka values. Their acid dissociation constant is less than 1. And there is an exception for sulfuric acid because sulfuric acid, which is H2SO4, it is a strong acid. And by a strong acid, what I mean is when you put it into water, it ionizes 100% to produce H pluses, and then it produces HSO4 minus. Well, HSO4 minus, it can then ionize a second time to produce another H plus and SO4 with a negative 2 charge. But this, in the second case, HSO4 minus is a weak acid. In other words, it does not go 100% to the products, or almost 100%. Whereas strong acids, their equilibrium constant for them ionizing in solution is so large, we ultimately assume that for strong acids, the reaction goes to completion. Essentially, this goes 100%. Whereas for the hydrogen sulfate ion, it dissociates, depending on the situation, typically less than 10%, oftentimes less than 1%. And figuring out exactly how much it dissociates will be the focus of a lot of calculations that we do in this unit with equilibrium. When we're talking about this, there's one other thing that I want us to look at. It's something that's easy to get a little confused about, and it's this thing called H plus versus H3O plus. H plus is called a hydrogen ion or a proton, and H3O plus is called hydronium. Now, here's the thing. H pluses don't actually exist on their own, but H pluses in the presence of water turn into H3O pluses. This reaction goes 100%. So anytime we're talking about them, these terms are used interchangeably for the same thing. For instance, for this reaction up here with sulfuric acid, I could have written it as H2SO4 reacts with water to make H3O pluses plus HSO4 minus. I could have written it that way. The reason that you don't typically see it that way is because since water is a liquid, it doesn't appear in the equilibrium expression. And so it's oftentimes easier for us to just ignore the water. But acids and bases, for the purposes of this class, we're only dealing with ones that exist typically in aqueous solution. So the water is there. We just oftentimes omit it from all of our equations for simplicity's sake. Yeah. Just also to define what a Ka expression is, and this appears on your reference tables. For any reaction HA is our hypothetical acid, and the H represents the hydrogen, and the A represents the acid part. It breaks apart into H pluses and A minuses, or really it reacts with water to make H3O pluses and A minuses. The Ka, the acid equilibrium expression, equals the H pluses times the A minuses over the HA. All right. I just fix this little there's a little issue with the formatting in this Google Slides presentation. Now, there's a list of some acids that you should know. Really, we've talked about these before at the beginning of the school year. There's the strong acids you need to know: hydrochloric acid, hydroiodic acid, hydrobromic acid, sulfuric acid, perchloric acid, and nitric acid. Those are the strong acids. If it's not one of those six, it's a weak acid. Your weak acids include hydrofluoric acid, acetic acid, carbonic acid, phosphoric acid, sulfurous acid, and any other acid that the College Board could throw at you on an AP exam, or that I could throw at you on a test, or anything else. They're weak acids, but they all work the same. The H's in front act as the acids. Now, some of these are called polyprotic acids because they have more than one hydrogen that can act as an acid. And we'll talk about those later. The calculations get a little tricky because they ultimately can ionize 2 or 3 times and have 2 or 3 Ka values. Bases. Um, Strong bases, group 1, strontium, barium, and calcium hydroxides, although generally we can just simplify this and say if it's a group 1 or a group 2 hydroxide, the bases that you should know. Our strong bases are group 1 and group 2 hydroxides. Please remember, hydrogen's not actually part of group 1, so hydrogen hydroxide, aka water, is not a strong base, obviously. And the weak bases are any other hydroxides, anything else that could accept a hydrogen ion. NH3 is a very commonly used weak base. NH3 reacts with water to form ammonium hydroxide, NH4 pluses and OH minuses. All right, so those are the bases. Bases typically, under the Arrhenius model, they have hydroxide in them. But as you'll see, it's anything that can react with an acid to accept a hydrogen ion is a base. Now, all of this ultimately revolves around something called Kw, which is the dissociation constant for water. And so for this, water, hydrogen hydroxide, can ionize into H pluses and hydroxides. Or if you want to think about it in a more technical standpoint, ultimately what's happening is water reacts with water to make H3O pluses and OH minuses, if you want to be really fancy about it. Right. But we just kind of simplify this and we just look at one water molecule doing it. And the Kw, the equilibrium constant for the ionization of water, it just includes the H pluses and the hydroxides because the water itself is a liquid and we don't include it. And it equals 1 times 10 to the minus 14th at 25 degrees Celsius, or room temperature, if you will. And when we talk about acid dissociation constants and base dissociation constants, ultimately, if you multiply them together, they equal the Kw. There's this thing called the pKa and the pKb. The P means negative log. We'll talk more about this a little bit later. But the negative log of the Ka plus the negative log of the Kb of a conjugate base equals 14. This is if you have an acid base conjugate pair. So we'll talk more about those later. But ultimately, this reaction right here is the basis of all acid base chemistry. It is the most important reaction in all of Unit 8. Because if you add acid to water, it will take this equilibrium position and shift it to the left because acids produce H pluses. So you're going to shift the equilibrium for the water dissociating to the left. And so as you add H pluses, your hydroxides will go down because of the common ion effect, if you remember it. Or if you have water and you add a base, you're adding hydroxides to that water, that's going to shift the equilibrium position for water to the left. And that's going to cause the H plus concentration to decrease as you add hydroxides. And that ultimately becomes the basis of our pH and pOH calculations. So pH is the negative log of the hydronium ion concentration. In other words, however much molarity your H plus is, you take the negative log of that, we call that pH. pOH is the negative log of the hydroxide ion concentration. pOH equals the negative log of OH minuses. And because of our equilibrium constant expression, if you were to manipulate this and you take the negative log of both sides of this expression, and then you remember that if you take the negative log of two things that are multiplied together, you can separate them and add them. The negative log of H plus is called pH, the negative log of hydroxide is called pOH, and the negative log of 1 times 10 to the minus 14th is 14. So pH plus pOH equals 14. And I can work that out for you if you need to see that real quick. If we take a look at the expression that H plus times OH minus equals 1 times 10 to the minus 14th. We take the negative log of that. Well, when you take the log of something of 1 times 10 to the minus 14th, you're really just taking the exponent. And the negative log, we take the negative of that, so that's 14. And you could split this up into negative log of H plus the negative log of OH minus. And then this is called pH. This is also called pOH. And they add up to 14. So if your pH is 5, your pOH is 9. If your pH is 11, your pOH is 3. If your pH is 7, your pOH is 7. Those things have to be the same. Or not the same. They have to add up to 14. So if we have a scenario where the pH is 4, well, then we know the pOH is 10. We could also find our H plus concentrations and our hydroxide concentrations. Let me make that look more like a 10. Our H plus concentration is 10 to the negative fourth, and our hydroxide concentration is 10 to the negative 10th. In other words, 10 to the negative fourth, 1 times 10 to the negative fourth is 0.0001. And our hydroxide concentration, that'd be 0.0000000001. So really small values that we're working with there. All right. Now, something that's very important to note about the pH scale is that it is a logarithmic scale. In other words, as you go from a pH of 5 to a pH of 4, your acidity increases by a factor of 10. If you go from a pH of 5 to a pH of 3, your acidity increases by a factor of 100. Because if your pH equals 4, Then your H plus concentration is 10 to the negative fourth, or as we already said, 0.0001. If your pH is 2, your H plus concentration is 1 times 10 to the negative 2, or just 0.01. So that's a factor of 100 difference between a pH of 4 and a pH of 2. So it's a logarithmic scale. So a little change in pH number is a huge change in acidity or basicity of your solution, right? So it's a logarithmic scale. Just to kind of wrap up a few things about this, H plus equals 10 to the minus pH, OH minus equals 10 to the minus pOH. And then you might already know this, neutral substances, their pH and pOH are 7. Acids, pH is less than 7, pOH is greater than 7, and bases are the opposite if you're at 25 degrees Celsius. Tomorrow we'll talk about what happens if you're not at 25 degrees Celsius. So hopefully this is a little bit of a refresher for you. You should have seen this before in previous chemistry classes. Also, if you have not looked at your reference tables on the front page of your formula sheet under equilibrium, all of these formulas are there. So please look for them, know where they are, and be able to access them in that manner. Right? If you have not looked at your AP chemistry reference tables recently, you should probably do so because on there you will find the Ka expression, the Kb expression, the Kw expression, and the calculations for pH, pOH, and that pH plus pOH equal 14. Uh, don't worry about these formulas down here right this minute. We'll get to them a little bit later. But these formulas are here. They do not include the formula for undoing pH calculations. You just need to know that this is how you would undo a pH calculation. Instead of typing negative and log on your calculator, you would type in the 10 to the negative. So you just press second log and then the negative button. That's how you undo a natural log. So I hope that helps. I'm going to have some practice for you to work on, and y'all have a great day.